Hello, the following video is a recording from our astrophotography workshop held within MetaJungle Discord. This class was originally held on January 27th and is taught by Mustafa Aiden, who's an accomplished astrophotographer and active MetaJungle member. This workshop is covering deep space astrophotography and is our part 2 of this particular series. And in this class, we're going to be covering planning, setting up, and shooting. And Mustafa does a great job of providing some hands-on examples along with software that you'll be wanting to use if you're interested in performing this type of photography. So we definitely appreciate all that Mustafa has put into preparing for this class and hope that you find it useful.
Okay, then let's start. So, deep sky astrophotography, we will be talking about a little bit of planning because our previous lessons had planning. It's more or less the same thing. We will be using Stellarium software to make the planning, to choose which deep sky object or objects we are going to shoot during the night. And if we are going somewhere to shoot our deep sky astrophotography, of course, we will have to again simulate the place, the hour, the date in Stellarium, and see what target or our target, what time it starts rising, and at what time it sets. And like I said, we will be using Stellarium for that. I will not go into detail with that because we already discussed. And again, we have to have a look at the weather forecast all the time. If you remember, we have this Clear Outside application. It is available for iOS and Android phones, and also a website. You can directly put the name of your city or your GPS coordinates to find the weather forecast. And this Clear Outside is especially designed for astronomers and astrophotographers because it has lots of information there for astrophotographers. And of course, if the place we are going, if it is the first time we are going, we have to check the light pollution using light pollution applications or light pollution websites. We, depending on what kind of astrophotography we will be doing, we have to check light pollution and make sure that it is not light polluted area. And we have to check our equipment before we go, just not to see some surprises there, because sometimes you go all the way to a few hundred kilometers. For instance, once I saw a friend who forgot his laptop and he had to drive back home, which was 300 kilometers away. So you have to check your equipment before leaving and make sure that everything works perfectly. And you have to prepare your camping gear if you are going out, and your tent, your sleeping bag, your sleeping mat, and everything. And of course, food. So this is from last summer. I was preparing for camping. So you will see how I am loading the car. And as you can see, my car is a very small one and it has a very small trunk. So it needs some Tetris game abilities to fit everything inside. So let's watch. Most of the time, back seat and the trunk is full. Yeah, that's the tripod and some other gears. And those are the kitchenwares and foods. Yeah. So once you're ready, you hit the road, and this is a very nice place that we used to go with friends, and there are times that I camped here for 10 days, and it is, if you remember about the light pollution, it has border three skies, which is fairly dark. There is also facilities that you can use. There are houses. There's another building on this side here that you can use the facilities. And if you want, you can sleep in a bed for a night because they have rooms. And let's see how I set my equipment up. Oops. I'm not explaining because right after this one, I will go on a webcam and do the job. And you can see my friend Murat is going back and forth. He's also setting his equipment. He's like my best friend. We founded the Ankara Astronomy Society together. Yeah, it's almost finishing. And my daughter was the one who was holding the camera because I also take her camping most of the time. She loves camping. Okay, so I will stop this and I will go on webcam. Hello, everybody. So tonight I wanted to do this because I wanted you to see what is going on, how it is set everything up. Um, Here you can see the tripod. We start with the tripod. You see this? There is one thing here. This tripod, when you put on the ground, it should look at north more or less, uh, because we will be setting the mount towards uh, north, celestial north pole. That is why starting in the beginning, we have to put it towards north, because after setting it up, because the thing is so heavy, the mount is so heavy, it will be hard to change the direction. So we will start with this piece here. This is Atlas, Orion Atlas Pro equatorial mount. So I start with this piece. And then we have this plate goes right here. And we want the mount on the tripod. Okay. So next, we have the telescope, and I need to show you this. This is a refractor telescope, if you will remember from the previous lesson, which has a lens glass here. It has 70 millimeter of diameter, and it has very special coatings to avoid chromatic aberration. And it has here, this piece here is a power splitter. I will receive the power from here and split to camera, div heaters, and other peripheral devices from here. And there is a USB hub here to collect all the data from different devices. And then we will have another cable directly goes to the computer. And here we have the auto guiding system. This is actually another telescope, and this is another camera for auto guiding system. And this orange and white strap here is a div heater. When you open it up, when you turn it on, it will hit the glass in front. And there's also a div heater here, this green thing. So it will hit the glass and avoids avoid div to happen. And we have here a dummy battery. This will go into the camera, and we will give power to the camera by this, so that we won't have to change the battery few times at a night. And we have here the USB data cable, which will go into camera also. And here, this red part is called dovetail bar, which will help us connect our telescope to the mount. So that's what I will do now. Okay, our telescope is connected to the mount, and I will take the caps off. Next thing we have here, this piece is called PaulMaster. It is actually a small telescope with a CMOS sensor in it. This will help us make the polar alignment very accurately, which is extremely important to be able to have very accurate auto guiding and also very accurate tracking. So I will explain why. And this goes right in front. And here we have a shaft for see, this is what I mean. Something is not working. Interesting. I don't know why. It looks like it jammed because there has to be a shaft coming out so that I could put the counterweight here. This is called counterweight shaft, but it's not working. So this is what I meant. You have to make sure that everything goes. Okay, I will not do it because I don't know why. There's something wrong. And then we have the cabling. First of all, we have two power cables. This is for the mount. It goes right here. You're not able to see it, but there's the socket here. And there's another one for power splitter. So now I can see here that power splitter has power. And here we have another cable because I'm going to connect the camera right here. To connect the camera, we have something called a tearing, and also for this, this may change from brand to brand. We have a tearing and also M48, M42 adapter. This will go to here. It will be screwed. And then we have the camera here. And we have the camera data cable. And we have the dummy battery. I'll try this once again. I don't know why it doesn't. So interesting. I don't know why it's maybe it's stuck. It's jammed because of something. I really wish I could open because I want to show you. Okay, and another thing here, we have this is also a weight, counterweight, to adjust the balance. Because this thing here, the mount has some gears inside. This has to be balanced. We will do it in a moment. This has to be balanced in both axes, not to make any unwanted power on the gears, not to broke them. And this is actually the second counterweight, but I cannot open the shaft of it, so I will not be able to do it. At this point, we have to lose the axes, and it will go like this. As you can see, that there used to be counterweight here to balance it, but I cannot do it because there is no counterweight because I cannot take shaft out. Any damage or accident, I will not open that. And I will do the cabling. Here we have, this is called ASCOM or EQ mode cable. This is an interface to make to be able to control the mount directly from computer. So we have ASCOM slot here, and I will connect to USB hub, and then we will connect this to directly to the computer. And we have here the cable for PaulMaster. And last, we have one last cable to connect everything to the computer from USB hub right into the computer. Okay, so actually this is more or less set up, except the counterweight. I will try once again because I really wanted to show some action here. Yes, it came out. So here the counterweight goes in here. Okay, actually, yes. So I will now loosen the axes. So we have two axes here. This one is called the right ascension axis, and this one is called right ascension axis. So we have to make sure that this stays in balance. You see, it falls. It shouldn't fall. It should stay like that. So to make sure, we will have to play with the counterweight to make the balance. Here also it doesn't work. So let's start with this one. It's not going to work like this because I need to push the telescope a bit further. Okay, so let's see now. You see, in this axis, it stays still, so it doesn't move. So this is what we want actually. It shouldn't be moving this way or this way. Also, in this axis, we want it, so it should stay still wherever we leave. So this is more or less okay. Maybe I can move this a little. So you see, it is on. It's on balance. So I lock the axis. There are two axes, and I lock both of them. And this position is actually called park position. Telescope is in park position. And also, before we do anything else, we have here a bubble level. This tripod and the mount should be level to the ground. And I'm looking at it, it's almost perfect because it is at home and the floor is flat. So there is no problem. So, and I will turn on the camera. Now everything is connected to the big computer, and I will turn my camera off, and I will keep the camera. I will show you. First of all, now can you see my screen?
Yeah.
Okay, so first of all, we will connect computer using the EQ mode or the ASCOM interface. Here, I opened the softwares beforehand. So once I click here, connect. So it is trying to connect. It will not connect because I didn't turn. Yes, now it is okay because I didn't turn the mount on. So I connect. And here we are connected. And this is our ASCOM interface. We have this. For instance, we can change. For instance, I am now in Gölbaşı. I click this one, and this will bring my GPS coordinates and my elevation. And I will set it here so that my mount will know it is in Gölbaşı at the moment at this latitude and longitude and at this elevation. And now I can show you that I can move the mount by using these buttons. You see, I can control my mount directly from my computer. I can slew on the both axes, right ascension and declination axes. So once I set park to home position, it will go back to the park position. And here we also want to open up a Stellarium program because we will be using Stellarium to make our mount to go whatever target we want. Okay, so I also will take this one here, but we won't do anything at the moment. And first thing that we do here, this is the PaulMaster software. We connected, and because if we were at night and if we were outside, we were going to see stars here because it is more like a telescope with a CCD CMOS sensor behind. So we were going to receive real-time images from the PaulMaster device, but of course we cannot see it. Instead, I will show you this. So here I'll share my. So this was the, as you remember, this was the ASCOM EcoMod interface. And why we were doing this, you will remember from last week, these equatorial mounts, the telescope plane is parallel to the Earth's rotation axis. So we want to make this parallel structure very accurate. That's why we are using this PaulMaster device and the software. And you will see here, this is like, this is the hemisphere around us. This is north and this is south. We call this imaginary arc meridian, and we call this point, the top point, zenith, and we call this point celestial north point, pole. So the celestial north pole is actually, you see, if we have a needle from South Pole to North Pole, this needle would be showing the celestial North Pole. So we want our telescope, we want our mount to be aligned perfectly to this axis. And this celestial North Pole is actually the latitude of the place that you are at the moment. For instance, here Ankara is almost 40 degrees, the latitude. So I will see celestial North Pole at 40 degrees. So that will give me my latitude actually. So I will have to align this accurately to this celestial North Pole. And this is the device that we are using, and this is the software. If we were outside and if we were seeing the sky, we were going to see, this is Polaris, the North Pole star, and this actually also revolves around the celestial pole. It's not at the very center. It's not at the very place where the celestial North Pole is, but we use this North Pole star, Polaris, and the other stars to align our mount to celestial North Pole. This has very easy steps. There's directions here. It says double click on the Polaris, double click on another star, move the mount in right ascension, blah blah, and then after 4 or 5 steps, and also you will have to use some knobs here on the mount. You will be able to very accurately make the polar alignment. And it actually polar aligns your equipment, your mount, in arc minutes, arc second level. So an arc second is an angular measurement equal to 3601 of a degree, which is, or 1/60th one of an arc minute. So it is very accurate. And next thing that we, after we are done with the polar alignment, we will have an image acquisition software. And as I use a Nikon camera, I use a software called Backyardnikon. So it has an interface like this. I put this one to show it better, but I will go and show you on the screen now. You can change this to red light so that your eyes will not be tired and will not be blinded. So let's go and see the real Backyardnikon. And here you can directly connect your camera by clicking on connect. So it is connected. And you can also connect to your ASCOM driver to be able to control some other things and oops, see, there's always something wrong. In astrophotography, there's always something wrong. I don't know why, but it doesn't connect to the ASCOM. Anyways, we will not need it for the moment. It doesn't see the ASCOM. It doesn't see the mount, actually. Okay, we will not need it. I was going to open that to show the detail. This is something that we always use. And we can change it to night vision, so it will look like this. It will not tire your eye. And when you look outside of the computer, you will still be able to see things. So here, we will talk about framing and focusing. In the first place, we will talk about focusing. So when I click here, frame on focus, this will actually live view from the camera and the telescope. But of course, again, we are not outside. We will not be seeing anything. But now I will show in the slides. There are different ways of focusing, and I will show them now. Okay, here actually, in our telescope, we have two knobs here like this. And this black one here is the focusing ring, and this one is even finer focusing. So, and this one here, there's a pin here. You can pin this down to lock the focuser system, or you can just open it up so that focusing system would work. So check, it's locked. So I don't know if you can see, but this will start moving outside so that I can make the focusing. So for this, like I said, we have I will show three different types of focusing element. First one is called FWHM focusing. By using star profile, and you see this is a star profile, and the half maximum, FWHM, is the abbreviation for full width at half maximum. So this is full width half maximum. This is actually a measurement of the star that you are seeing, the diameter of the star, and the program will measure for you, and you will see as you are playing with your focuser rings, you see here we have FWHM value. So it is 64 now, it's too high. By playing our focusing ring, we will of course pick a star here, and we will watch FWHM value, and we will make it as small as possible. If you will remember from the previous lessons, I was showing you how to make focus using a live preview on your camera. So we were playing with the focuser ring, and when the star is out of focus, it is bloated and it's fat. And once you get closer to the focus, you were seeing that star was getting smaller and smaller. So we will also see the same thing here. So we will point our telescope to a bright star, and we will pick the star, and we will start with the focuser rings. First the black one, then the blue one to have the finer focus. And we will watch FWHM. And when the FWHM value smaller than 2, we will accept that we are on focus. Of course, that value will change depending on the seeing that day. You may not be able to get the same FWHM value in 2 consecutive nights because of the weather changes. Maybe there will be a high thin cloud, or maybe there will be some turbulence on the atmosphere. So this is the first focusing system. And yeah, we can see here, if the FWHM value is high, the star will look like this. It will be bloated. And when you, sorry, when you go and reduce the FWHM value, you will see the star gets sharper and more focused. And the next focusing system is called Bartender Mask. I have a Bartender mask here. This is a Bartender mask. So as you can see, you can also see here, there are some holes. These holes will create star spikes on your star. And when you play, and again, you will open your image acquisition program and software, and you will see the star that you are aiming. And when you're out of focus, you'll see these star spikes will not align perfectly, like here. This is inside focus, so you still have to get your focuser system outside. And once you're on focus, your star will look like this. All the star spikes will be aligned perfectly. And if you pass the focus point, then it will again go bad like this. The star spikes will not align to each other. So this is also a very, very easy method to use. You can either use Bartender mask or FWHM values to get perfect focus. And here I wanted to share a website. Here there's the link, and this is the screenshot of the website. You can actually put your values, your focal length, and your outer diameter, inner diameter, and create a Bartender mask. And you can download as SVG file that you can print using a 3D printer. So it is so easy. You can do this with your lenses also. If you want to shoot night sky with your lenses, you can easily create a Bartender mask and print with a 3D printer. There are other websites, and also there are some applications that you can use create Bartender masks. So if you Google it up, you will find it easily. And the third one is better, also more expensive one. That's why we call astrophotography never-ending purchasing, adventure. If you purchase one of these, uh, different brands have different models. So this is actually goes right into the focusing system of your telescope, and there is a stepper motor inside it. And by using a software, you can move the focus system forward and backwards, and it will draw a graphic like this. Here, this time, it will use another value called HFR to again measure the diameter of the star. And you see it starts from here, goes down, goes down, goes down, and it comes to this point. This is the point where the star is on focus, and it will go up like this. And then it will come back and stop here. So if you adjust this device, it will go and it will go and check your focus during the night a few times. But for the other, um, the first two previous methods, you will have to do this manually if there are changes in the conditions, like if there is change in the seeing condition, if there is a thin cloud, you will have to do the focusing manually once again if your focus go bad. Oops. And something happened. Anyways, and framing. For this, I will again go to Stellarium. So you see here it says Atlas Pro. So that this is the name of the mount. Stellarium is now connected to mount directly. So it is showing, you see, this is Polaris. It is showing the North Celestial Pole. So when, let's say, I want to shoot, let's say, Elephant's Trunk Nebula. So it's not far from Celestial Pole. And I will open my FOV field of view. So using this telescope and this camera, this is my field of view. When I shoot, I will see this. And once I click, I have to click this first. Once I click Control-1, you see telescope started going there. Of course, we assume that telescope is aligned perfectly to the North Pole, because it is not at the moment. If it was perfectly aligned, this was going to go here, and then we were going to go to Backyardnikon, and we were going to see some stars, not the, of course, nebula, but we were going to see some stars from here. For instance, we were going to see this star for sure. It is called the Garnet star because it's the brightest star here. And then we were going to do the framing. We can use something called plate solving, and this software is capable of doing that. We could have snap an image, and this program, the software, was going to go and compare the image that it has just been snapped with the database, and see if it is at the correct place. If not, we were going to fix, and we were going to make the framing using Stellarium and also Backyardnikon. Yes. So once the framing is done, so we were going to use Stellarium, and we would do the framing. We could use a high ISO and very short, like 10 seconds, 20 seconds frames to see if you are on the right place. And if you are not, we could still go and use this. Where is it? Here. We could make small adjustments using these buttons, controlling the right ascension and declination axes. And once we have the framing, and next thing is auto guiding. Again, if you all remember from the last week, this thing here has gears inside. So when it is tracking the night sky, of course, the movement from the motor inside will be transmitted by using the gears. And gears, even if they are manufactured perfectly, they have backlashes. So those backlashes will cause some inaccuracy in tracking. And why we are tracking? To have pinpoint stars. So we will see if we want to go on like 5 minutes, 10 minutes exposures, we will see that our stars starting to get elongated. And that's what we don't want. That's why we use this we use this additional equipment called auto guiding system. This is used with a software called PhD2, and also here you're looking at a telescope and also a camera. This is called guide scope, and this is called guide camera. And the guide scope should be at least 1/3 of the focal length of the original imaging scope. So when you're choosing your guide scope, you have to know that it should be 1/3 of the, at least 1/3 of the focal length of the imaging scope. And these cameras are sold as guide cams or planetary cams. Most of the guide cams are also used as cameras to shoot planets and moon. And to be able to use this, we have a software called PhD2. So you see, and actually I will go to the PhD2 here. So it was open on my computer. So I was going to connect, and so I connect to the guide cam and the mount, and I say connect all. And when I click here, we'll see a white screen. Why? Because we are inside the room and guide scope is open. So we were going to see stars near our target because this telescope is parallel to the original imaging telescope. So we were going to select the star, not the brightest one, not the dimmest one, and we were going to say auto select star. It will not be able to select the star here. It was going to select the star, and then we were going to calibrate this because this program was going to move the mount and move star from the axis onto different sides and see how it is reacting. And because this program will be sending commands to the uh, mount if the mount goes too fast or goes too slow. And we were going to see some graphs here, and it was going to be like this. So see, we were going to see some graph here, and blue graph uh, refers to right ascension axis, and the red one assigned to declination axis. And after the um, calibration is done, these two lines turns green like this. And during the whole shooting session, we were going to watch this all the time, and we were going to watch actually this left bottom corner. We have something called RMS error. We have the right ascension RMS error and declination RMS error. What we're going to watch was total RMS error. And we always want this number to be as small as possible to have perfect guiding. So, but we aim less than 1. But smaller, the better. So once we are done with auto guiding also and get auto guiding running, so like I said, throughout the night, we will always watch this value. And if we see this value goes up, then we will know there is something wrong. And we will also watch the graph. There will be crazy movements here. So what can be the problems? For instance, a cable might jam, or some high thin clouds may come, or someone can hit the mount, and these all outside effects will get the auto guiding bad. So we don't want anything to happen. And if there is something happening, we will understand from here. But if there is something going very wrong, auto guiding will start beeping, and then you will understand that there is something wrong. And that is the sound that none of us want to hear during the night. So that will mean something wrong. And once we are done with the auto guiding, because that was our last calibration and adjustment, we will come back to image acquisition program, and we will start shooting. We will start shooting some trial frames. You see, you have here a type. It is written light because we have different types of frames. The light frame is the actual frame of the object, and we were going to get the shutter bulb. And here we can change the duration, and here we can change ISO. As you can see, we can control our camera without even touching it. with this program. So I will go and yeah, here. So if we go here to imaging, and you see, you can say that I want to shoot 20 of light frames. So you see light, bias, dark, flat, dark, flat. These are the types of bias, dark, flat, and dark flats are called calibration frames. The light is the original uh, photo, and we were going to use bulb, and we can adjust our exposure time, exposure duration using here, and ISO. And are we going to have a delay uh, before the first shot? Let's say we can say after 2 seconds you can start, and the pause will, let's say, if you say 2 seconds, it will put 2 seconds between each frame, so that you can leave your sensor cool down a little between the frames. And of course, here in the settings, you can adjust. You can select the you can select the file name. You can select the quality. You can say RAW plus JPEG, or just JPEG, or in camera. Uh, so it will save the files inside the um, memory card, but we don't do that. And uh, and we can also select the folder that the uh, files will be recorded. Okay, so when we say apply and save, and when you say start capture, it will start capturing 20 light frames at 1600 ISO at 180 seconds of exposures, and save it to the folder that we told software to save. And we were going to see it like this, actually. I prepared some light from here. So when we start shooting, we were going to have lots of frames here, and we can always go and check, zoom in and check how the stars look, if there is an elongation or not, if there's something wrong. And we can right click here, we can pick if the frame is good, maybe bad, or delete. For instance, let's say if we had elongated stars here, we could go and say delete, and see in the folder it is marked as delete. So if I go and say good, it will be marked as good. Yes. And of course, we watch here the histogram to make sure that our exposure and ISO values are okay. As you know, in telescopes, there is no diaphragm, that you cannot change the opening of the telescope. It is standard, and this telescope here has 350 millimeters of focal length and 70 millimeter of aperture, physical aperture. So divided, if you divide 350 to 70, you will get 5, which is the F ratio, F5. But uh, if it was a photography lens, you could change that F number. Uh, you could go down. but in telescopes you cannot do that. And we are going to watch the histogram, and the correct histogram, if we have a histogram right on this line, we will say we have the right exposure. Our image is not underexposed or overexposed. But here you can see red, green, blue channels are separated from each other. The reason for that, this image here was shot with a special filter, and it separates the channels. But during the post process, you can fix this, so you wouldn't mind. So here, while I was shooting this target, I was sure that the red channel was on this line to be able to um, see that um, my exposure time and ISO settings were correct. And here we have the same image shot with Nikon D5300, 300 seconds, 1600 ISO, a light frame. And then we have dark frames. Dark frames are used for eliminate the thermal noise because you see 300 seconds, during the 300 seconds, your sensor is going to be hit by lots of photons, and it will convert those photons into electrons and um, collect those electrons in within the pixels, and this will cause some heat. And you see these red, green, blue dots. They're actually the thermal noise. And we shot dark frames to eliminate, to subtract the image, this noise, from the original image, to have with a less noisy image. So this here uh, has five 300 seconds dark frames. They are stacked on each other, so it is called master dark. And this is going to be subtracted from the original image. This is what we call calibration or pre-processing. And we have also bias frames. Bias frames are shot at the fastest exposure, shutter speed in your camera. And this shows actually the noise from the camera, the electronics of the camera other than the sensor. So those electronics around the sensor will cause some kind of noise called bias noise. And shooting bias frames and shooting lots of them, and again stacking them, and then subtracting this from the original light frames will give you less noisy image. And last, we have flat frames. You see, this is one single flat frame. You see here some dots. These are actually what we call dust bunnies. These are dust pieces stick on your sensor. If you don't keep your sensor clean, then you will have this type of dots. And you can also see some vignetting. You see towards the edges, it's darker. So to eliminate these dots and the vignetting, to have a evenly distributed image at the end, we also shoot flat frames and subtract from the original image again. And this is 70 flat frames stacked, and as a result, we have a master flat. this will be calibrated with the light frames. And here we have the final stacked image of 27,300 images, light frames, and dark frames, bias frames, and flat frames calibrated and stacked all each on top of each other. And this is it for tonight. And if there are questions, I would love to answer.
No, I don't see any questions.
Okay. So I hope it was fun to see the equipment also. So let's park the telescope. This is actually the fun part. When the night ends, you know, you say park telescope and go to bed. Okay, thanks for listening.
Thank you, Mustafa.